In this lesson, we're going to talk about the graphs of polar coordinates. So when we're talking about the graphs, we're going to look at symmetry often. So in the symmetry, the graph of a polar equation has the indicated symmetry if either replacement produces an equivalent polar equation. So there's two replacements for each. If you want to test for symmetry about the x-axis or the polar axis, you're going to replace the point r theta with r negative theta or negative r pi minus theta. You're going to talk about symmetry about the y-axis. You'll replace it with negative r negative theta or r pi minus theta. And if you want to test for symmetry about the origin or the pole, you'll replace r theta with negative r theta or r pi plus theta. Okay? So these are important to know and to memorize. So let's look at a couple examples. Say I want to prove that r equals 4 sine 3 theta is symmetric about the y-axis. So for symmetry about the y-axis, we're going to replace r theta with negative r negative theta. Alright, so we're going to place r with negative r, and then we have 4 sine 3 theta, so it'll be 4 sine of 3 times negative theta. Okay, so this leaves us with negative r equals 4 sine of negative 3 theta. And now we can remember that sine is odd. It's an odd function, so that negative can be brought out front. We can divide both sides by negative 1. We'll be left with r equals 4 sine of 3 theta, which is what we started with. So it is symmetric about the y-axis. Alright, so let's look at the second one. So we want to prove it's symmetric about the y-axis. So we can start with the same thing. We'll replace r theta with negative r negative theta. So r is replaced with negative r. We have 3 plus and then 3 sine of negative theta. Sine is odd, so we can bring that negative out. And there's not much else we can do here, and so this tells us nothing. It's not saying that it's not symmetric. It's not really telling us anything. So let's try and replace r theta with the other equivalent, which was r pi minus theta. Okay, so r goes to r, then we have 3 plus 3 sine, and then replace theta with pi minus theta. So now we're left with r equals 3 plus 3 times. Now this is the difference of angles. So we have sine of pi, sine of theta, or cosine of theta, sorry. And then we have minus, because sine, when we're using the difference of angles, sine stays the same. So cosine of pi, sine of theta. Okay. Now from here, we have r equals 3 plus 3 times sine of pi, cosine of theta. Sine of pi is 0, so this becomes 0. Minus cosine of pi, sine of theta. Cosine of pi is negative 1, so we have minus negative 1 times sine of theta. Simplifying, this gives us r equals 3 plus 3 sine theta, which is indeed what we started with. So this is in fact symmetric about the y-axis. So since this one really wasn't telling us much, we had a negative over here, we had a negative over there, we're not really sure what is similar, what is different. We try the other substitution, and we can see that it is in fact symmetric about the y-axis. So you want to make sure you're testing both of them if your first option does not work out. Alright, so the next polar equation we're going to look at are rose curves. Now rose curves have the equation r equals a cosine n theta, or r equals sine a sine n theta. Now n is an integer greater than 1, okay? So if n is even, and we're looking at our sine, r equals a sine n theta, the graph is offset. The petals are not cut by the axis. So that means you'll have two petals, and they'll be on either side of that axis. That means, and then if it is odd, it is symmetric about the y-axis. Now if you have r equals a cosine n theta, the graph is on the axis, so the petals, the axis actually goes straight through the petals, and it is symmetric about the x-axis. If you're looking at the number of petals, you have 2 n petals if n is even, and you'll have just n petals if n is odd. So if you have a cosine 3 theta, n is odd, so you'll have 3 petals. If you have a cosine 2 theta, n is even, so you'll have 4 petals. Okay? So you want to be able to look at your function, look at the graph of it, or look at it, whether it's even or odd, and tell me what the graph looks like. So we'll look at an example. We have some general characteristics of a rose curve. The domain is all real numbers, and this is looking at the angle. This refers to theta. Okay, so all reals is all angles. Our range is the negative absolute value of a to the absolute value of a. So that was that first part here. So your range is negative absolute value of this to the absolute value of it. It is continuous. If n is even, it is symmetric about the x-axis, y-axis, and the origin, all three. And if n is odd, then cosine is symmetric about the x-axis, and sine is symmetric about the y-axis. Okay? So if n is even, you're going to have symmetry about all three. If n is odd, you'll have symmetry about either the x-axis or the y-axis. It is bounded, and the maximum r value is the greatest distance from the pole. So here the greatest distance you can get away from the origin is a. So we want to look at r equals 2 sine 3 theta. So to do this stuff, we want to graph it first. So to graph a polar function, we have to go into mode, and we're going to change our mode to polar. So we're going to make sure POL is highlighted. So here POL is highlighted, I'm good to go. I'll hit y equals, you'll notice you'll have r's instead of the y's. So we're set to graph this. We have r equals 2 sine of 3 theta. So I already have this put in here, 2 sine of 3 theta. Theta can be found up here where your x, t, theta button is. So you want to make sure you're pressing that. Same place you found your x for your linear equations. Now we want to graph it. So to graph this, we're going to use zoom 7. That's going to zoom into our trig window, and that'll give us a decent sized graph. So we can see that this graph looks almost like a clover. So n is odd, it's got 3 petals. So we can draw this right in here. Looks something like that. So I used zoom 6 or zoom 7 to get that window. So now that we have our graph, we're going to look at the domain. So the domain is going to be all reals. Or you can write negative infinity to infinity. Our range is going from the negative absolute value of our A. So absolute value of A is 2, so -2 all the way up to the absolute value of A, which is 2. It is continuous. You can draw the whole thing without picking up your pen. Symmetry. Its symmetry is about the y-axis. So you can reflect it over the y-axis and it matches. That's because n is odd and we have sine. So when sine has n odd, we're symmetric about the y-axis. It is bounded. And the maximum R value is A, which is 2. Alright? So for this one we can see that since n is odd, this axis is going n is odd, so it's reflected over the y-axis, and it'll match up. Since we're looking at sine, the graph is not cut by that x-axis, okay? It looks like it's cut by the y-axis, but when we're talking about which axis it is cut by, we're talking about this x-axis, okay? So it's not cut by the x-axis, it is offset. So that's why we know it is sine, and then n is odd. Alright? Now we're going to look at some limacon curves. So for limacon curves, you have the equation r equals a plus or minus b cosine theta, or r equals a plus or minus b sine theta, where a is greater than 0 and b is greater than 0. Some general characteristics are the domain is all reals again. The range is going to be your a minus b and your a plus b. It is continuous. For symmetry, if you have cosine of theta, it'll be symmetric about the x-axis. Sine theta will be symmetric about the y-axis. It is bounded. And the maximum R value is the greatest distance from the pole is going to be a plus b. So these are some things that you could memorize, be able to analyze these functions very quickly. Something special about limacon curves is there's 4 different shapes. So the 4 shapes of a limacon curve is there's a limacon with an inner loop. And we can see that here we have a over b is less than 1, and a is greater than b. So an example I picked is r equals 1 plus 2 cosine theta. So my a over my b is 1/2, which is less than 1. A is 1, b is 2. So a is less than b. And it gives us this inner loop inside the curve. For a cartiod, you have a, here I picked the equation r equals 2 plus 2 cosine theta, a equals 2, b equals 2. So we can see that a over b is equal to 1, and a is equal to b. And this is what you're going to get. So you can think cartiod. And it's heart-shaped. Okay, so that's an easy way to remember this one. It's heart-shaped, a cartiod, and then everything is equal. So now we'll look at a dimpled limacon. The equation I picked here was r equals 3 plus 2 cosine theta. So here my a equals 3, my b equals 2. So my restrictions for this one is a over b has to be between 1 and 2. So a over b is 1.5. 3 over 2, so it is in fact between 1 and 2, and I get this sort of dimpled effect. It kind of looks like a mushy Pac-Man, whatever you want to try and remember it as, but it's got a big huge dimple in it. The last one is a convex limacon, where a over b is greater than or equal to 2. So my a equals 6 and my b equals 2. So my a over b is 3, which is indeed greater than or equal to 2. And the result is something that looks like a lime. So you think convex limacon looks like a lime. So those are 4 types of limacon curves. Some of them will look a little bit different, but they'll all have the same general shape. So that is it for this lesson. Some important takeaways. are the 4 different shapes of the limacon curve, the general characteristics of a limacon curve, the general characteristics of a rose curve. For rose curves, if it's even, the axis is not going to cut sine theta. If it's even, the axis will cut the petals of cosine theta. If it's odd, sine is symmetric about the y-axis, cosine will be symmetric about the x-axis. And then being able to prove the symmetry by replacing r theta with one of these two values for the x-axis, proving symmetry about the x-axis. To prove symmetry about the y-axis, replacing r theta with one of these two. And to replace r theta with one of these two to prove symmetry about the origin or the pole. So that is it for this lesson.